here I have graphing rational functions, and with the rules I had talked about earlier about asymptotes, right? Vertical, horizontal, holes. Really, we can use those rules to successfully graph various rational functions. So you may be given something like f of x is equal to x plus 3 divided by x minus 4. A relatively simple problem here. So looking at this, you always want to look at these 6 different criteria, really, or 6 different factors. If you can find the answer to each of them, really you can graph your rational function. So this, again, horizontal asymptote, holes, vertical asymptote, x-intercept, y-intercept, and really your domain. So for which values is the equation defined, right? And for which values is the equation not defined? You should be able to differentiate between those two sets of values. So looking at this, we have the horizontal asymptote, and the rule states that, again, if the degree is the same, which in this case it is, right, of the leading coefficients, it's 1 and 1, you do a over b, and a over b represent the leading coefficient. So that's just 1 over 1. That is 1. Therefore, this indicates that there's a horizontal asymptote at y is equal to 1. So that's the horizontal asymptote. That's where your graph is approaching, right? It's not going to hit that, but it's going to approach that, or it tends toward that asymptote, really. So with the holes, though, again, that's something that can be removed. Really, that's where the concept of removable discontinuities comes from, because that's where, when you talk about holes, that's in the form of x minus a, which can be simplified, or which can be cancelled out from the numerator and the denominator. But looking at this has no holes, because unless x plus 3 in the numerator was being multiplied by x minus 4, then it would make sense for you to say that x minus 4 cancel off, and therefore there's a hole at 4. But here, obviously, there's no. So really, we say that this is not applicable. So not applicable. And now looking at the vertical asymptote, really it's about setting the denominator to 0. So if we set x minus 4 to 0, we see that there's a vertical asymptote as at x is equal to 4, and that makes sense, because really an asymptote is where the function is undefined. So no matter what happens, the function will never hit that. However, later in the later lesson, I will be going over why your function may in fact cross your horizontal asymptote or your slant asymptote. However, a vertical asymptote cannot be crossed, and that makes sense, because if you have x is equal to 4, there's really nothing you can do. It just gives you a 0 in the denominator, which overall makes the entire value undefined. Now going with the x-intercept is the value of x when y is set to 0. Really, when y is 0, or when f of x is 0, the numerator must be 0, right? Because if the numerator is 0, then you divide that by anything, it won't matter, it's going to give you 0, right? So that means that x plus 3 is 0, therefore negative 3, comma 0 is your x-intercept. And the y-intercept is the value of y when x is set to 0. So substituting 0 in for x, we get 3 over negative 4. So that's just 0 comma negative 3 over 4. And now when we talk about our domain, right? Our domain is a set of all real numbers. It's always for any polynomial rational function, really talking about all real numbers. However, so you can write this as a set of all real numbers such that x cannot be 4. And it probably makes sense why x cannot be 4, right? Because if x is 4 here, it gives you an undefined value. But for all the other values, it does satisfy, so it includes all other real numbers. Now we have to graph this, and so let's look at this. So if this is your x-axis and this is your y-axis, so let's think about this. We know our asymptotes, right? There's an asymptote at y is equal to 1, so that is this. You could say that that's y is equal to 1, right? And then you also know that you have another asymptote that is vertical at x is equal to 4. X is equal to 4. However, you don't have any any hold, so we can just disregard that part. But we know the x-intercepts and the y-intercepts, right? We know that the x-intercept is -3 comma 0, so we can make an approximation. It may be something like this. And then we know our y-intercept as well. That's 0 comma -3/4. Now we don't have to be really exact on where our values are, but this gives us a good approximation because we know that our graph is approaching these asymptotes. If we know that these 2 points are part of that graph, we can make our graph here, especially in this zone here. So we would just continue, and then continue, and continue here. So this over here, right? I mean, this clearly shows that with these 2 points, you're guaranteed that your graph looks something like this. Again, these lines are going to approach. As you continue to go down, the graph will approach that asymptote, but will never actually touch it. So this is one part of the graph here. Now, with the other part, now you don't have any other points. However, you can obviously substitute values in, right? You know here that this asymptote here is a vertical asymptote at x is equal to 4. So you know that's x is equal to 4, and really you want to see if any point lies here, because if it does, most likely your graph will be something like that, and you're done, really. And to check that, we want to take some value of x that is obviously greater than 4, so we can really check which points exist when x is greater than 4. So let's just take something like 6. So if x is equal to 6, right? Let's say if x is equal to 6, then we do 6 plus 3, that's 9, and 6 minus 4, that's 2. So that's something like 4.5. Clearly, 4.5 would be somewhere here, or something like that. And so if that is where 4.5 is, we know for sure that our line or our graph must be something like that. Something like that, right? Where this is ongoing. So this is our sketch here. Using these different rules, we have graphed this function over here. And so in the next lesson and other lessons, I will just give more examples and sort of guide how do you exactly graph various rational functions. So thanks for watching.